So our first part of today is going to be a review of stuff you did in 9th grade. And I know you did it in 9th grade because I taught it. It's called linear regression, lines of best fit. They are also called trend lines. Those three words all mean the same exact thing. So if you remember back in 9th grade, also remember in science class, your line of best fit goes through where? The middle of your data points on your scatter plot. It's basically kind of like an average of all of your data. Gives you that line of best fit. No. And then we can use the line of best fit to be able to predict some values from it. So oftentimes in science class, a mathematical relationship between two variables is desired for predictive purposes. In the real world, the relationship between the two variables is not always a perfect one. So we look for the best curve possible. And again, that best curve possible is just a prediction of where should you be at that given time. That doesn't mean it's the only place you can be. It's just a prediction of this is approximately where you should be. So first example, we have a pediatrician would like to determine the relationship between infant female weights versus their age. So the pediatrician studies 100 newborn girls and finds their average weight at the end of 3-month intervals. The data is shown below and graphed on the scatter plot. So now for some reason, my points on my scatter plot are actually off a little bit. So let's fix those up a little bit. So 0, 7.2, each line represents 2. So 2, 4, 6, 7.2 should be about there. We got to fix our points. And then 3, 12.2 would be about there. 6 and 15.1 there. 9 and 19.4. 12 and 21.5. And 15, 26.3. Right there. So those are our new data points. So using a ruler or any kind of straight edge you have at your desk, I want you to draw a line that you think best fits this data. As a general guideline, try to draw it such that there are as many data points above the line as there are below the line. So that's what our line of best fit does. It goes through the middle, so you want to have equal numbers above and below. And let's see here. Oh, I'm going to use my little line tool here.
We don't have a little line. So use the line.
So part B, by picking 2 points that are on the line, not necessarily your data points, just 2 points that the line goes through nicely, determine the equation for your line of best fit, round your coefficients to the nearest tenth. So your line equation might be slightly different than mine, but we're still going to follow the mx plus b format because we do have an equation of the line. So first thing I need to figure out is my slope. So in order to figure out slope, I need to find 2 points. Looks like my graph goes through that one and that one. Nope. I got 6, 7, 2, 4, 6, 8, 10, 12, 14, 16. I got 7, 16, and 10, 20. Those are my 2 points. Again, your 2 points are going to be different. It depends on what your line is. So find 2 points on your line, and then find your slope. Nope, because your line doesn't necessarily go through the table. It's an approximation. So I got a slope of 4/3. I don't know what your slopes were. Okay, which is 1. So we got to find our b value. So I'm going to use one of my 2 points. And I'm going to plug that into my equation with my slope. Calculate my b value. Again, your b values are going to be different. Let's see here, gives me 28 over 3. Subtract 28 over 3.
Yeah, we're looking at 16. Oh, yeah.
From my point. Yeah. So I got a B value of 6.7. It told me to round things to the nearest tenth, so I changed my slope back to my 1.3. Should be the decimal form. So I got my equation to be 1.3x plus 6.7. Again, yours is going to be slightly different. I'll give you a second to finish it up. Part C wants us to use our linear regression command on our calculator to find the true equation for our line of best fit. We're going to round all of our parameters to the nearest tenth. So in your calculators under L1, you're going to type in the age in months. Under L2, you're going to type in the average weight in pounds. Oops, those in the wrong place.
How high up are we going on that L1?
Just what's in the table. So we are going to do our linear regression. So if you go to Stat, over to Calculate, choice 4 is your linear regression. They shorten it down to linreg. So get 4 and hit Enter. Some of you may have your list where it should say X list is L1, Y list should be your L2, and then everything else should be blank. So enter, enter, enter. And you should get this. So it always tells you at the beginning what the basic equation is. So our basic equation is y equals ax plus b. And then it gives you the values of a and the values of b after that. So, part C, using our calculators, what is our a value to the nearest tenth? 1.2. So we got 1.2x. No, there's a 1 after it. And then 7.8 is our true line of best fit. Hey, I wasn't off by that much. I had 1.3 and 6.7. Anybody else really close from their equation?
Mine was so off. My slope was 7 over 11, and I had -2.
Yeah.
That mean it?
No baby is born at -2 pounds.
Yeah, exactly.
Just saying. All right, so using your calculator to determine the linear correlation coefficient. So our correlation coefficient, that is the R value in the calculator. Now, if your R value is not showing up, that means we have to turn on your stat diagnostics. So to do so, push your mode button, and then you'll arrow down, and you should find in your list stat diagnostics, and you want to turn those on if they are not currently on. What? Leave the wizards alone. No Harry Potters today. Stat diagnostics, those need to be turned on. All right, so now, if your R value didn't show up, all we have to do is run our linear regression again. So stat over to calc choice 4. and then your correlation coefficient will now be there. So to the nearest thousandth, what do we get?
0.996. 0.995.
0.995. So then they want to know, how can you interpret this value in terms of the variation in weight due to age? So our correlation coefficient always is between -1 and 1. And the closer you are to -1 or +1, the stronger the relationship is. So is our value close to 1? Yeah, very close to 1. So we can say there is a strong positive correlation between age and weight. So as I was saying, even if it's like -0.995, that just means there's a strong negative correlation between the two things. But because it's close to -1, it would be a strong relationship. The closer it is to 0, the weaker the relationship it is. So exercise 2, using the equation that your calculator produced in exercise 1, predict the weight of a baby girl after 10 months. Round your answer to the nearest tenth of a pound. So our equation was 1.2x plus 7.8, right? Somebody flip over on the front to see if my memory's right.
Yeah, you're right.
I hope so. So 10 months. We'll put the 10 in for the x because age was our x value. So let's figure out what it's predicted that a 10-month-old baby should weigh. 19.8. So the use of a model to predict outputs that are within the range of the data you are provided. So like, for example, 10 months falls in that range because they gave us data from 0 to 15 months. So 10 falls in that range. That's what we call interpolation because it's inside the data, inside. It falls within our range. So now we're going to use the equation, and we are going to predict the weight of a baby girl after 2 years. Round your answer to the nearest tenth of a pound. Now 2 years, though, we need it in terms of months. So how many months? 24.
Now this wouldn't be accurate because we stopped being made at 25.
False.
For the most part. Well, yeah, but you don't like exponentially gain like they do.
This isn't exponential, this is linear.
You just don't consistently gain like 20 pounds.
But this isn't saying they're gaining 20 pounds every month.
Yeah, but if you gained how much they did every month, it would be like 700 pounds.
It slows down eventually, but not when they're babies.
If your metabolism, yeah.
How much is our 2-year-old girl going to weigh? 36.6 pounds. Now, I will say that's not completely accurate because, for example, my 3-year-old doesn't even weigh that much yet. So the use of a model to predict outputs where the value is outside of your range is known as extrapolation. So that's when you're going beyond the data set that you are provided, you're extrapolating. So models are most helpful when they can be used to extrapolate, but they tend to be a little less accurate. So as I was saying, this model is helpful. However, it's not 100% accurate because 36.6 is a little high for a 2-year-old. All right, let's look at exercise number 4. Biologists are trying to create a least squares regression equation, which is a fancy name for the line of best fit, relating the length of a steelhead salmon to their weight. 7 salmon are measured and weight with the data given below. So here's our 7. So what I would like you to do, type this into L1, type that into L2, come up with your equation for our linear regression. So what do we get to the nearest hundredth? There we go. 1.33x minus 27.98.
Why is it a negative?
because if this was 0, I mean, there's no fish.
Oh,
So
that's true.
the fish doesn't exist. All right, so using your equation from part A, determine the expected weight of a salmon that is 30 inches long. So let's plug 30 inches in for our x. And let's see what we get. So 1.33 times 30 minus 27.98. Type it into that nifty invention called the calculator. All right, so what do we get for the weight? 1.92 pounds. It's a pretty big salmon right there. All right, so next one wants us to figure out how much it should weigh if it has 52 inches long. So plug it in, plug it in. 1.33 times 52 minus 27.98. That's not what I got. That's what I got. Oh, yeah, no, 52. All right, so in which part, B or C, did you use interpolation? And in which part did you use extrapolation? So remember, interpolation means it's inside your data range. So which one was in between 22 and 48? B or C? It's C. B. So that means C was your extrapolation. All right, now there are other types of regressions. Linear regression, that was the first one we dealt with. There is exponential regression, there is quadratic regression, and there's sinusoidal regressions. So again, you just use your calculator, plug and chug. So here we have the populations of Jamestown has been recorded in the years since 2000. The table below gives these populations. So they want us to, using your calculator, determine your exponential equation. They told us which kind to do. Where x represents the number of years since 2000 and y represents the population. Round a to the nearest integer and b to the nearest thousandth. So since it says x is the number of years since 2000, you're not going to use 2002, 2004, 2005. You're going to use 2, 4, 5, 7, and 9 because it's the years since 2000, not the actual year. So then go ahead, type this in your L1. Type this one in your L2, and this time you're doing an exponential regression. So rounding a to the nearest integer, what do we get? 5,157.92. So 58, because we want the nearest integer for a. So 5158.
Oh, round b to the nearest thousandth.
B is to the nearest thousandth. A is to the nearest integer.
Okay, this is an example for the clips.
Directions and details. Read the directions and details. So now b to the nearest thousandth is 1.041. To the x. B wants us to sketch a graph from the years 2000 to the year 2050. So my x, I'm going to go from 0 to 50, because remember they're talking about years since 2000, not the fact that it's 2050. For the year 2000, That was our initial starting. So remember, A is your initial starting value. So that means in the year 2000, the population was 5158. So I'm going to put that on my y-axis. What was our population in the year 2050? We don't know yet. Oh my God, guys, you don't. What could we do to figure it out? Plug 50 in for X. It's amazing. So let's again go to the nearest integer. I don't know. I'm pretty sure I got 38461 earlier too. 5158 times 1.041 to the 50th, 38461. Yep. So I'm going to put that also on my y-axis up toward the top. So now since we are simply sketching, does it have to be 100% accurate? No. So is this going to be a straight line? No, because it's exponential. So 0 is going to start here, 50 is going to meet my 38,461, and then I'm just going to make my little Fitchah graph and connect the two. My Fitchah graph. All right, part C, by what percent does your exponential model predict the population is increasing per year? Explain. So again, reviewing our exponentials, you get your percent increase from the B value. We would get the B value by adding 1 plus the rate. So 1 plus the rate is how we get our 1.041. If I subtract my 1s, my rate is 0.041. So as a percent, 4.1%. What's missing from my answer? Explain. The B value is 1 plus rate. So subtract 1 and move the decimal. So for part D, it says algebraically determine the number of years to the nearest year for the population to reach 20,000. So we're going to say that we want 20,000 to equal our equation. So we need to solve for x, which is our number of years. How do we get x out of the exponent spot? Divide first by the 5158. Now don't actually divide yet and get a decimal because we want to try to get exact value for our answer. So leave it as the fraction for right now, 20,000 over 5158. So now, no. How do I get x out of that exponent spot? This was like your favorite unit ever. You gotta take the log of both sides.
Oh.
So the log of our fraction, which is 20,000 over 5158. When I take the log of the right side, that makes my exponent come down in front. So it's x times the log of 1.041. Then we need to be studying. So now how do I get the log of 1.041 away from my x? Divide. Yes, we do type log in the calculator. Log button, remember, is over here on the left underneath x squared. So we would do the log of 20,000 divided by 5158 and close that parenthesis up. And then that's divided by the log of 1.041. Enter. So to the nearest year, 34 years. All right, question number 2. Which of the following scatter plots would be best fit with an exponential equation?
3.
Got one person voting 3.
Boom.
It would be 3. What kind would choice 1 have? That's a log. That would have a log regression. Logarithmic regression. How about for choice 2? What kind of regression? Linear. And choice 4? Linear. So sometimes looking at the scatter plot and seeing the trend of the data lets you see which kind of regression you're going to need, because you can kind of see the shape of your data. All right, last kind, sinusoidal, also known as your trigonometric regression, is much more complicated than the other ones. It should be used in situations that appear periodic in nature. Remember, the periodic means that it just keeps repeating the same cycle over and over and over again. So the temperature of a chemical reaction changes during the reaction. The temperature was measured every 2 minutes, and the data is shown in the table below. So why does it seem like this data might be periodic? Create a quick scatter plot using your calculator to verify. If we look at our temperature, what is it doing? It starts going up, and then it starts going down, and then it goes back up again. So it's just following this pattern of it goes up and down, up and down, up and down. So in your calculator, type those into your L1 and your L2. So for your scatter plot, we need to go to second, y equals. That's where you get your list of your stat plots. You always want to use the first one. Don't use any of the other ones. So first thing we will do is we will turn the stat plot on. So hit enter for on. And then for type, you want to make sure you've selected a scatter plot, because that's what we're trying to make. So that first one should be the one that's picked. X list should say L1, your Y list should say L2, and then the mark, you can pick whatever mark you want the calculator to make to show you your data. Okay. So then once your scatter plot is turned on, all of your information is set. You're going to push the zoom button and then the number 9, and it creates your scatter plot.
You see, I told you it was 9.
Zoom and then the number 9. It is not quadratic. It is a sine curve. It goes up, comes down, and it goes up again, and then it'll come down, and then it'll go up again and down. It is a periodic function. It's a sine curve. Quadratic goes like this, and it keeps going down. It doesn't turn and come back up again.
Oh, wait, yeah.
No. All right. So why does it seem like the data might be periodic? Because it goes up, then down, and then back up again. So because it follows that periodic curve, using our calculator, we're going to do a sine regression in the form. Here is your basic equation for a sine regression. So you're going to get values for A, for B, for C, and for D, and then you just got to plug them into the equation. Now we already have all of our data in there, so all we have to do is push stat over to calc, and then your sine regression is choice C right there. It says sin reg. So you hit enter, enter. We're going to round to, let's see here, what is it? Nearest tenth. So somebody help me out. What's my A value to the nearest tenth?
3.9.
So 3.9 sine. Our B value to the nearest tenth? Our B value to the nearest tenth?
0.4.
C value to the nearest tenth?
Negative 0.7.
And D value to the nearest tenth?
38.5.
There you go. There's our equation. Plugged in A, plugged in B, plugged in C, plugged in D. So now see, according to this model, what is the range in temperatures the chemical reaction will include? So again, thinking back to trig, this is your midline. This was our amplitude. Your range is the midline plus your amplitude, and your midline minus your amplitude. So 38.5 plus 3.9 gives us, let's see here, 42.4. Let me check me. Add it in your calculator. See if the Pelkey brain's working today. 6? I think so. So there's our range. So 34.6 to 42.4. That's going to be our high and our low based on our model that we have there. That's our predicted high and our predicted low. So then D, according to this model, what is the time it takes for the reaction to complete one full cycle? Remember, one full cycle is what we call our period. The formula that none of you memorized for your test. B times P equals 2 pi. B is your frequency, P is your period, and 2 pi is what it always equals. B is what's ever in front of X. For the trig unit. Divide by 0.4. 2 pi divided by 0.4 gives us 15.7 minutes would be our period. So one thing I want to go back and do that we didn't do was we're going to graph the data along with our equation there. So in your calculator, so graphing calculators may vary. Many will require to type in a period in your sinusoidal function. If the period is unknown, like in our last example, we didn't know how long the reaction took. So we had even increments of data. We had 0, 2, 4, 6, 8, 10, 12. Gentlemen, stop it. Sometimes the period is known. So if it is known, you can type that into your calculator, like our last example here. The maximum amount of daylight that hits a spot on Earth is a function of the day of the year. Taking x equals 0 is January 1st. So that means that's January 1st. 34 days later, so that's like February 3rd. So on and so forth. They calculated how many daylight in hours was for that certain day. And they did that 12 times. So was the number of possible hours of sun from sun to day. So what is the natural period for our information here? If we're looking at the days of the year. How long does it take for the days of the year to repeat? 365. So our natural period, one full cycle, will happen every 365 days. Okay. So what I want you to do is I want you to type into your calculator your data, L1, L2, and then do your sign regression in your calculator. Those of you who have your list, you will type in 365 for your period. It makes your answer more accurate. So what do we get? Well, it's going to vary. Let's round the first one to the nearest tenth, because that one we can. So you should have 3.7 as your A. B, that one should be a smaller one.
Wait, we go sine reg.
Wait, what?
Yes, sine reg.
Calculate.
0.01.
All right, so B value, let's go a little further because that one's a very small decimal. So I'll put 0.0313x. C, negative 0.87. And then D is 11.6. All right, so we'll change those numbers, negative 0.83, 11.5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's what you had. Oh, you know why? 'Cause there's only 11 data points, and I said there was 12, so one's missing. I probably put all 12 in there. All right. So our maximum value, midline plus your amplitude, gives you your maximum value. So what is it? 15.2. Yep, hours. Now is that our actual max value?
Yeah.
Oh my God, it is! It's amazing. It works out.
OMG.